Section 4.2, Exponential Functions. An exponential function is any function in the form of f of x equals a times b to the x, where b is greater than 0, but b cannot be 1. And we also have that a is not equal to 0. We've somewhat looked at these functions in the last section. These functions were used to help us model exponential growth and decay. When a is positive and b is greater than 1, then f of x models an exponential growth. When a was positive, but b was between 1 and 0, then f of x modeled exponential decay. From our problems involving exponential growth and decay, we have an idea of how exponential function graphs should look. And there's generally two shapes based off the size of b. Now, on the right, there are two examples of the graph of f of x equals b to the x. Notice how the graph in green is decreasing, but getting closer to the x-axis and never crossing the x-axis on the right, while our orange line is increasing, but on the left-hand side, it's getting closer to the x-axis, but never crossing. The way we can determine whether it's increasing or decreasing is based off the size of b. If b is greater than 1, f of x is increasing and gets closer to the x-axis as we trace to the left. That creates the graph of what looks like an exponential growth problem. If b is between 0 and 1, then f of x is decreasing and gets closer to the x-axis as we trace to the right. And that's what we would expect from the exponential decay model. It would get closer and closer to 0 as x got larger and larger. One important detail to keep in mind about the graph of f of x equals a b to the x is that it will never cross the x-axis. So these functions have no x-intercepts. Next, we're going to take a look at how to graph f of x equals a b to the x. Because of how simple the shape of the graph of an exponential function is, we can plot f of x simply by plotting 2 points and then connecting the 2 points in such a way that it matches the graphs we saw in the previous slide. Now, the two numbers that are going to be very easy to work with in these problems is x equals 0 and x equals 1. The reason why these numbers are so nice is since b is never 0, then b to the 0 will be 1, and b to the first will always be b. So they're two numbers that are very easy to plug in and do calculations with. So if we take a look at f of x equals 2x, first we'll plug in 0 and evaluate f of 0, which would be 2 to the 0, which is 1, which means 1 point on our graph is the point 0, 1. Then we'll plug in 1, so we'll evaluate f of 1, which would be 2 to the first power, which equals 2. So our second point is the point 1, 2. Let's go ahead and plot both of these points, and we see the 0, 1 and the 1, 2. We know one side of the graph is going to rise to infinity, while the other part is going to get closer and closer to the x-axis. Taking a look at how we connect these points, as we go from left to right, it looks like we're going upwards. So let's keep that trend. Now, on the left, we're going to have to get closer and closer to the x-axis. But remember, we never cross the x-axis. And there's my graph of f of x equals 2 to the x. Next, we're going to plot g of x, which equals 1/2 to the x. First, we'll plug in 0, which would be 1/2 to the 0, which is 1. Then we'll plug in 1, so g of 1 will equal 1/2 to the first, which is 1/2. So we'll have the point 0, 1 from the g of 0 equaling 1, and we'll have the point 1 and 1/2 from the g of 1 equaling 1/2. Now we can plot the 2 points. There's our 2 points. I did make the 1 1/2 just a little bit smaller since we have a fraction as one of the components. But now looking at how we would connect these dots, notice how on the right this time, going from left to right, we're getting smaller. So the right-hand side should be getting closer and closer to the x-axis. But remember, never crosses the x-axis. Since the right is getting closer and closer to 0, then the left is going to rise to infinity. Look a bit like that. Now, a couple things to note, especially when our base is a fraction, there are several different ways to rewrite our exponential expression. So for example, the 1/2 to the x, our 1/2 to the x, thanks to our exponent properties, is the same as 1 to the x over 2 to the x, or 1 over 2x. So that's one way we can rewrite the 1/2 to the x. Or if we use the definition of negative exponents, 1 over 2 to the x is the same as 2 to the negative x. So that is two other ways we could rewrite 1/2 to the x. Next, we're going to graph f of x equals 2 times 3 raised to the x. But just like what we did in the previous example, we're going to plug 0 and 1 in for x. So first we'll find f of 0, which is 2 times 3 to the 0. 3 to the 0 is 1, and 2 times 1 is 2. Now we'll evaluate f of 1, which would be 2 times 3 to the first. 3 to the first is 3, and 2 times 3 is 6. So from the f of 0 equals 2, 1 point on the graph will be the point 0, 2. From the f of 1 equals 6, 1 point on the graph will be the point 1, 6. So now we'll plot both points on our coordinate plane. There we have 0, 1, and 1, 6. And now we're going to connect our dots. We can see if we trace from left to right, we should be rising to the right from how we would have to connect our points. And on the left, that part would have to be getting closer and closer to the x-axis. And there's my graph of f of x equals 2 times 3 to the x. Next, we're going to solve the following equations that involve exponential functions in Desmos. To start, we're going to solve 2 times 3 to the x equals 14. Going into Desmos, we'll start by typing in the left-hand side, which is 2 times 3 to the x. And in the second line, we'll type in our right-hand side. Now move around our graph just a little bit, and we can see a point of intersection right here at the point 1.77124. 14. One solution to this equation, rounded to 2 decimal places, is 1.77. How do we know for sure that there's not another solution? If I zoom out just a little bit, recall that our exponential graph are either strictly increasing or strictly decreasing. In order for our graph of our exponential function to intersect with our horizontal line, our graph would have to turn around somewhere in order to come back around to intersect our blue line again. However, we know this is impossible. Our graph specifically, 2 times 3 to the x, is always increasing. It will never turn back around in order to intersect our line. So x equals 1.44 is the only solution to this equation. Next, we'll solve 5 times times 1/2 to the x. So again, we'll type the left-hand side in first, then we'll enter the right-hand side. And we see from the graph, we have a point of intersection at -220. So one solution to this equation is x equals -2. No rounding needed here. How do we know that's the only solution? Well, as I stated in the previous equation, exponential functions are either decreasing or they're either increasing. Here, our exponential function is decreasing, and it can never turn back around to intersect the y equals 20 again. So there is only one solution. Now we're going to determine which table represents a linear function, an exponential function, or neither. Taking a look at our first function on the left, first we're going to see if our function is linear. Notice how our x's in our first table are increasing by 1, meaning I have to add 1 to the previous x to get the next x. In order for this table to represent a linear function, I would have to add the same value, whether that value is positive or negative, to the previous f of x to get the next f of x. Well, what would I have to add to 5 to get 7.5? Well, if we subtract the two, 7.5 minus 5, we get 2.5. I would have to add 2.5 to 5 to get 7.5. In order for this table to be linear, I should be able to add 2.5 again in order to get the next entry in my table. But 7.5 plus 2.5 is not 11.25. So I can't just add 2.5 to each of my function values to get the next function value. This means our function is not linear. Now we'll check to see if our function is exponential. To be exponential, that means when my x's change by a fixed value, my function values should change by the same factor, meaning I would multiply the same value to go from one function value to the next. Well, what would I have to multiply to 5 to get 7.5? To figure that out, we'll divide. If we do 7.5 divided by 5, we get 1.5 or 3/2. It is up to you which you want to multiply by. If you're using a calculator, typing in 1.5 is easier. If you're trying to do this in your head, the 3/2. Let's do times 1.5 just to make the writing easier. In order for this to be exponential, I would have to multiply the 7.5 by 1.5 to get my next function value. Well, if we check 7.5 times 1.5 is 11.25. So everything's looking good that our table might be exponential. But we do need to check the last function value. In order for our table now to be exponential, I would have to be able to multiply the 11.25 by 1.5 to get our last function value. Well, if we check with a calculator, 11.25 times 1.5 is 16.875. So our table represents an exponential function, since every time I change x by one value, my function value is changing by a factor of 1.5. Now we'll move to the second table. Just like before, our x's are changing in increments of 1. We'll start off by checking to see if it's linear. Well, what would I have to add to 5 to get 7.5? Well, we did do this earlier. We know we would have to add 2.5 to 5 to get 7.5. In order for this function to be linear, I should be able to get my next function value by adding 2.5 again. Well, if I add 2.5 to 7.5, I do get 10, which is my next table entry. And if I add 2.5 to 10, I get 12.5. So every time I increase x by 1, I increase my function value by 2.5. So my table represents a linear function. There's no point in me checking to see if it's exponential. There are no functions that are both linear and exponential at the same time. Now let's move on to the last table. Just like with the other two, my x's are increasing by 1. We'll start off by checking to see if our function is linear. We know what we have to add to 5 to get 7.5. We know that would be 2.5. Now, would adding 2.5 to 7.5 give us our next entry in the table? Yes, 7.5 plus 2.5 is 10. So far, it looks like it might be linear, but we can't conclude that until we check to make sure we can add 2.5 to 10 to get our last entry. Well, if I add 2.5 to 10, I get 12.5, not 11.5. So that is not good. Because I can't just add 2.5 over and over again every time I increase my x by 1, my table does not represent a linear function. Now we'll check to see if our table represents an exponential function. Well, recall from before, we know we have to multiply 5 by 1.5 in order for us to obtain 7.5. In order for our function to be exponential, I would have to be able to multiply the 7.5 by 1.5 in order to obtain our next entry. But 7.5 times 1.5 is 11.25, not 10. So multiplying 1.5 over and over again does not give me the next entries in my table. So this tells me my function is not exponential. So this table is an example of a function that is neither linear nor exponential. Next, we're going to write an exponential function in the form of f of x equals a b to the x, or the following table. The most important part of the exponential function that we first need to identify is b. If we think back to our last section, b is either the decay factor or the growth factor, depending on its size. This is the value I would have to multiply f of x by to get the next function value. If we take a look at our table, what would I have to multiply 4 by to get 2? If we do 2 divided by 4, we get 1/2. So to go to 4 to 1/2, so to go to 4 to 2, I would have to multiply by 1/2. Would multiplying by 1/2 obtain the other function value? Well, if I multiply 2 by 1/2, I do get 1. And if I multiply 1 by 1/2, I do get 0.5. So from this, I can see that my decay factor, because we are getting smaller, so it would be a decay, is b equals 1/2. So from this, I know f of x is in the form of a times 1/2 x. The question now becomes, what is a? To figure out a, I can take any one of the points that are presented in the table and plug it into my function. Looking at the 0, 4, because 0 is the easiest number to work with when it comes to exponents, we know that f of 0 would equal 4 from our table. Plugging 0 into what we know our function looks like so far, we have a times 1/2 to the 0 equals 4, 1/2 to the 0 is 1, anything times 1 is itself. So we get that a equals 4. Now that we figured out a and b, we now have our exponential function. Our exponential function will be f of x equals 4 times 1/2 raised to the x power. We can also use regression curves to help us figure this out in Desmos. If we make our table, enter our values. In line 2, we start typing in the regression curve command, y sub 1, tilde, and then the form of the function we want, a times b raised to the x sub 1. And here we see that a would be 4 according to Desmos, and b would be 0.5, which is the same as 1/2. So we could use the regression curve command to also come up with our function as well. Taking a look at the next table, this table here we saw in the previous example. Recall that every time our x coordinates increase by 1, our function value changed by a factor of 1.5, meaning to go from 5 to 7.5 to 11.25 to the 16.875, we had to multiply by 1.5. So here, b would be 1.5. And from this, we know so far, f of x is equal to a times 1.5 raised to the x power. But we still need to figure out the value of a. Since I know 1.5 is on my table, that tells me f of 1 equals 5. Well, taking 1, plugging into what we know about the function so far, we get a times 1.5 raised to the first equals 1. 1.5 to the first is just 1.5. So we get 1.5a equals 5. And if we divide by 1.5, we get a equals 10/3. Now that we know a and we know b, we can make our function. F of x equals 10/3 times 1.5 to the x. Just like with the last table, we could also use Desmos to find our function. Going into Desmos, we'll change the values in our table. Now that we have our table entered into Desmos for this particular problem, we can see our a is 3.3 repeating, which is the same as 10/3, and our b is 1.5. Here's how we can find the equation for our exponential function, either using algebra or using the regression curve fitting in Desmos.